We're going to start. Good morning, everybody. Thank you very much for coming along. My name is Bryan Hogan. Can I get a little show of hands of people who have heard of Poly before? This is so much better than previous conferences I've been to. And then, of you that have heard of it, how many are using it? Okay, a few less. And then, who's using retries? Fallbacks? Fewer. Circuit breakers? One. Ian. Bulkhead Isolation? Oh, no hands. Yeah, so that's kind of what we see. It's mostly retries and fallbacks. That's good to know. I'm going to have my Twitter handle up here. If there's time at the end, I'm very happy to take questions from the audience, or if you don't feel like it, you can tweet them at me. If I can't answer them during the session, I will happily look at it later in the day. So Poly, for most of you who are aware of it, is an answer to a problem that you have. But those of you that haven't heard of Poly, it may well be the solution to a problem you're not aware of. So failures happen. They can happen to any application at any time, and they will happen to your application. So what do you do when something goes wrong? Many of us are working on applications that rely on connectivity, but connectivity has never, ever been a guarantee. The old adage, the network is not reliable. We also have to deal with software errors. Some of us have to deal with things like local network outages, and of course, applications are now spread out across the internet, and you have to deal again with unreliable connections around the world. Any problem along the way could lead to your request failing. If you're working on mobile applications, this is especially true. So what can you do if there's a transient fault or a longer outage in a system that you rely on? You could do this. You could throw up a yellow screen of death. This might be okay if your application, if it doesn't matter to your application that you lose one request. This might be unacceptable if you're working in a banking scenario. But this might also lead to cascading failures if you have more and more failures. The question becomes, what can you do about a failure, like particularly a transient fault? And retrying is the usual answer. If, let's say, you're building your own little application, and it depends on a remote application, retrying would look a little like this. You make your first request, and you get a failure back, or you don't get a response. So you retry, and you get another failure. And you retry, and you get another failure. And then finally, you get back the response you were hoping for. You could keep at that an infinite number of times, but usually you will limit it. So how would you program something like that? And I've asked this is a good audience, you're all using Poly, so you know how to do it. But when I've asked this at conferences where people are not using Poly, the answer usually looks something like this. If you're making a request with a HTTP client, you do it as normal. You put a for loop around it, retrying 2, 3, 4, 5 times, whatever suits you. But you might get exceptions, so you need a try-catch along the way. You may have to catch multiple types of exceptions, or you might do a catch-all with plain old exception. And then you have to break out of that loop if you get a successful response. And people have tried to convince me that this is good enough, and this is usable, and they're happy to do it. But it's fragile. It's very, very hard to use in multiple locations. It's difficult to change. It's hard to customize. And of course, it's not what I would recommend. And here's the answer. Poly. Poly is a resilience framework for .NET. And if you are using Microsoft technologies, it is the only game in town. If any of you have worked in the Java world, you may have come across Hystrix. Hystrix has some of the features that Poly has, and it has a few extra ones, and Poly has some more features that Hystrix does not have. Poly helps protect your applications from failure, but this has a knock-on effect on downstream applications that are calling you, and on upstream applications that you depend on. It helps all of them to remain stable when faced with transient faults, longer outages, excess load, or other problems. Poly is able to do this through things like retries, wait and retries, circuit breakers I mentioned, and a few other features. Poly was started in 2013 by Michael Wolfenden, but more recently it's been taken over by the AppVNext group. And I think a few of you saw Carl Franken's presentation yesterday, so Carl is part of that. In the last few years, an English gentleman named Dylan Reisenberger has been leading the project and doing an enormous amount of development. The Poly project is active on GitHub, Slack, they have their own blog, and Dylan has been on both my own podcast and a little more recently on the .NET Rocks podcast. Poly works on all platforms that .NET works on. So think of how this might help your mobile applications, embedded applications, or IoT, where connectivity is more difficult. I'm going to show you all the code that you need at the point of making a request with Poly. So forget about that for loop, forget about the try catch, forget about the break. This is all you need to make a reliable request. I'm going to use my little pointer. So you have your HTTP client making a request to a remote endpoint, and you make the call inside a policy that you've defined, and the policy is a Poly retry policy. Again, at the point of the request, that is all the extra code you need if you are pre.NET Core 2.1. You do need to define the policy ahead of time, but you do that once for your application. What this policy says is that it works with HTTP response messages, and if the status code you get back is anything other than a success code, or there was an exception, you retry up to 3 times. You still get back a HTTP response message. It doesn't interfere with what you're getting back. You don't have to unwrap anything, unbox anything. This is easy to reuse, and it's very easy to change and pass around. But if you're on .NET Core 2.1, that's all you need at the point of making a request. Notice how there is no reference to Poly, there's no execute async. You use your HTTP client as though Poly wasn't there. You don't even have a using statement in that class. You don't have to pass the policies around, and this is all thanks to HttpClientFactory. I'm going to have a few slides on that a little bit later. A few years ago, when I started work on a Pluralsight course on Poly, I couldn't find any definitions of what a resilience framework was. So when you're in that kind of position, you come up with your own. And I have 3 points. The resilience framework actively protects resources. It restricts the amount of memory, threads, sockets in use, and it makes use of caching and other capabilities. When possible, it will let you recover from a failure, so things like retrying, wait and retrying. But if recovery is not possible, it will facilitate graceful degradation. That could mean failing quickly rather than slowly, depending on your application. It might mean reducing the load on yourself or an upstream application, or shedding load, or returning some sort of default. It's very context dependent on your own application. So what graceful degradation means is for you to decide. But again, think of how this might have upstream and downstream effects. I'm going to repeat this a few times throughout the talk, as I want to kind of drill it in. Because you make your own application resilient, you are helping those that call you and the ones that you're calling. And you'll see examples as we go through. Poly is broken into 2 broad categories called called strategies. There are reactive strategies and then proactive. The reactive strategies are the ones that most people have used here. The retry, where you make a request, it fails, and you retry immediately. A wait and retry, which as the name implies, puts in a little bit of a pause before the retry occurs. A circuit breaker, this one cuts the connection between your application and a remote application that may be struggling. And a fallback. This will return something when everything else has failed, or it will take some action that is of use to you. That could be paging someone, sending an email, scaling out a system, rebooting a computer. That's entirely up to you. And of course, dependent on the context that you're in. On the proactive side, these ones monitor ongoing events and attempt to prevent problems before they occur. They'll try to stabilize your system and allow it to fail more gracefully. The first of these is a timeout. This one lets you decide when a request should not continue. You want it to stop after 5 seconds instead of 20 seconds, which would be the default, say, for some applications or for some libraries you're using. Caching will store a response for a period, and then if another request of the same kind with the same parameters comes in, Poly will read from its cache, return that, rather than make an outbound request. And then Bulkhead Isolation. This one protects resources, so a failing part of your application or a part that's struggling won't consume all the resources of your application. It won't consume all the threads, memory, sockets, database connections, file I/O, whatever it happens to be. At the heart of Poly are policies. So the things that we've been talking about, retry, timeouts, circuit breakers, they're all policies. A policy is made up of two parts: a handles clause and a behavior clause. So just to remind you, that's what a policy looks like. This is the handles clause. It specifies the conditions under which the policy becomes active. So in this case, if you get anything other than a success code, the policy is active. And this is the behavior clause. So if I get back a 500, I'm going to retry up to 3 times. I won't retry more than that, and I won't retry if I get back a success code on the first retry or the second retry. As you can see, they are written in a fluent style. Policies are also reusable. A single policy can be used in many parts of your application. You could pass it into controllers with dependency injection. There's also a thing called a policy registry, which I will cover in a few slides. Or with .NET Core 2.1, you can pass it around via HTTP clients that come out of a HttpClientFactory. Policies are thread safe. So a single policy can be used in multiple places at the same time. So if I've got a retry making a request to GitHub and I have a retry making a request to Google, the counts are independent. They don't interfere with each other. You can use a single policy simultaneously in 100 places. All policies support the execution of delegates. Retry has an on retry. Fallback has an on fallback, which allows you to perform another action just before the retry executes. So this is very useful for reauthorization. So imagine you make a request, you get back unauthorized. There's very little point in making the identical request 3 more times. You want to perform some sort of reauthorization. And I'll show you an example of that shortly. You can use policies with both synchronous and asynchronous code. They come in 2 flavors. And policies can be wrapped. What this means is you can have a policy inside a policy inside a policy, which then finally executes something like a HTTP client request. So an example might be a retry, which is retrying a HTTP request. The retry is wrapped by a circuit breaker, and the circuit breaker is wrapped by a fallback. So in a case like that, you'd make your request. If it fails, you'll retry a bunch of times. If they all fail, the circuit breaker will consider cutting the connection. It may not do so, but then the fallback will return some default for you. For the rest of the talk, I'm going to be coming back to this particular slide. So this little green piece of code is my representation of our application that we're going to be building for the next 40 minutes or so. And I'm going to try to build up a picture of a fault-tolerant application that can stand up to the kind of failures we talked about at the start. The first thing I think we need is the ability to make robust requests. So in the event of a problem with a remote system, my application should retry. I may want to be guaranteed to get a response, even when there's a failure. That isn't always the case, but I want the ability to do that. I want to be able to cut the connection to a remote system that's failing or responding too slowly, because I'm going to reduce load on it and help it, and I'm also going to help myself. I would prefer to fail quickly rather than slowly. Why take 100 seconds to fail when you know you're going to fail after 1 second? Again, I'm going to reduce local resource use. I'm going to help my downstream system that's calling me, and I may help an upstream system. If I can use a cache for requests that are the same within a short period, again, I'm going to help myself and help all the applications around me. And then I should also protect my own resources so that one part of my application can't do damage to other parts of my application. So an example might be you're getting incoming requests that you need to make outbound requests for, and you're getting thousands and thousands of them, and that part of your application is now going to suck up all your sockets, and you won't have any sockets left for a different part of your application. We can prevent that with Poly. This slide is going to be a quick overview of how a general request works. Most of this is HTTP client oriented, but it applies to other types of things too. You make a request, you check if it's a success. If it is, you return your nice response. If it's a failure, you still return a response, and you may have to handle it in some fashion. Maybe you do, maybe you don't. Maybe you're happy to return the 500 to your caller. With Poly, it'll change slightly. So we make our request as normal. We check its response. Poly will kick in if it's a failure. Poly will then determine whether or not you should perform a retry. So I might say, I'm only going to retry 500s. I'm not going to retry unauthorized. If I am going to retry, then I'm going to make a request again. If that one happens to be a success, I return my response. If the retry fails, I come back to Poly. I check again whether or not I should perform a retry. You may, because again, the failure might be one that you're handling, or you may not, because you might have already hit the limit of retries and you're going to give up, and you return a response. Poly doesn't interfere with the flow of a request when it succeeds or when it fails. It's only when it's a condition under which it should be active. But having said that it interferes, it doesn't do anything to the response. It doesn't change it in any fashion. It's only that it will retry it in a fashion, in some form. And as I said earlier, you can use a single policy to concurrently make hundreds and hundreds of requests. And they don't interfere with each other in any way. But there's a problem with retries. And it's this. If the system you're calling is failing because it's already overloaded, and you're going retry, 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 you're not helping. You're not giving it any chance to recover, and you're going to overload it even more, and it's going to take longer for that system to get to a point of responding to you. But you're also making life worse for yourself. You've got lots of open sockets, lots of threads, lots of memory in use. A slightly better solution is to use the wait and retry policy. You make your request, and you pause if it's a failure. You pause, let's say, for 2 seconds, and you retry. If that's a failure, you pause for 4 seconds. Now you're giving that remote system a chance to recover, and you're also not in any way using up your resources at a very high rate. And then you might wait 8 seconds, and then finally 16 seconds. You can choose any algorithm you want for that delay. It's a little lambda, which I'll show you in a moment. So you can do it as 1 second, 2 seconds, 3 seconds, some 2 to the power of, as I use in this case. And as I said, this gives the remote system a chance to recover. If any of you have done networking, you might know Ethernet uses something like this when packet collisions occur. There's a small problem with this. So if you are making thousands of outbound requests to a remote system, or hundreds even, and they're all suddenly failing, and then all your requests are waiting and retrying at the exact same rate, then you're going to be sending out hundreds of requests at 0 seconds, and at 2 seconds, and at 4, and at whatever it is, 8, 16. But what you can do is, in the little lambda to determine how long you should pause before making a retry, you can put jitter in. So you could say 2 seconds, 4 seconds, 8 seconds, plus or minus, random number, no greater than 300 milliseconds. And now all of them are going to back off at slightly different rates. So the likelihood of you hammering that remote system is reduced. I want to show you a little bit on how the two of them look. So we looked at a basic retry earlier. This one is one less line. So it's a retry policy, and it's handling HTTP response messages. If the status code I get back is not a success code, I retry up to 3 times. The wait and retry looks almost identical. Same condition. If it's not a success code, I wait and retry up to 3 times. And in this case, I'm going to delay, and this is my little piece of code for my delay. So you can see you could choose any algorithm you want for the wait and retry. If you're on .NET Core 2.1 and beyond, you're probably going to use HttpClientFactory and dependency injection. So you're probably going to define your policies with IAsync policy as opposed to the named type. But for the rest of the presentation, to make it easier to read, so it isn't IAsync when you're looking at it, I'm going to stick with the defined types. I'm going to use retries instead of IAsyncs. But it would be the slightly better approach for a real program. I mentioned earlier that reauthorization is a particular case with retries. You don't want to retry if you get a 401 back. You need to do something. And this is where the onRetry delegate comes in. So the start of it is the same. I'm checking if it's not a success code. I'm going to retry 3 times, but this is my onRetry delegate. And I can get a little bit more granular now. The onRetry delegate, this particular one, requires me to pass in the response and the retry count. I'm not going to use the retry count in this case, but I check the status code of the response, and if it is unauthorized, I perform some some reauthorization logic. Of course, it's up to you to decide what that is. It could be getting a new cookie, renewing a JOT, grabbing something from a database, but then your next request will now hopefully be reauthorized. Performing reauthorization when you're using HttpClientFactory is more complicated. I have an example on my blog, and there'll be links at the end, or you can quite easily find them on Twitter. I'm going to give a very quick overview of how the general policies work, and then I won't be showing these kind of slides again. As we saw, poly only gets involved when there's a failure. It will determine whether or not it should perform some action, and if it should, it takes that action. In most cases, like we've talked about, it would be a retry, but in other cases, it could be cutting a circuit, it could be sending a fallback, it could be cutting communications, shedding load, those kind of things. So request, checks the success code, should I get involved, should my policy get involved? No, let the request continue, return the failure. Yes, my policy should get involved, take some action. At some conferences, people have asked me, can I use poly for other things? And I hadn't included a slide like this up until a few months ago. And yes, you can. You can use poly for any type of code you execute. You can execute any method you want with it. In this case, I'm executing some error-prone code that returns a number. I'm executing it inside retry policy, and the retry policy says that it's going to expect an int type. If the int is not 0 or a divide by 0 exception occurs, retry 3 times. So you can use poly for any type of execution you want. Another little example. In this case, I'm going to look for some sort of job status. I expect an enum back. If my enum isn't valid, then I wait and retry. And then a final one would be, I'm going to execute some code that's going to throw an exception probably, and all I have to do is handle an exception and I'll retry it 3 times. You can use poly with database requests, with file I/O, with connections to the cloud, anything you want. I've primarily used it for HTTP requests because that's what I work on, mainly API to API communication. But it will work with anything. All right, back to our little application. So we've achieved what I would say is robust requests. So our application is getting a little bit more fault tolerant. On to the next one. So fallbacks are the policy that you're probably going to use last. If you're using them in a wrap, especially, they're going to be at the outside. You could use them with retries, you could use them with caches, you can use them with circuit breakers, you can use them pretty much with anything, but it's almost always going to be the very last policy you use. It can be used to return a default. It can be used to return a cached value, but poly has its own cache, so that's probably not the best thing. But it can, as I said earlier, it can be used to perform an arbitrary function through the on fallback delegate. So you could page someone, scale a system, reboot a system, scale up a database, anything of that nature. You aren't limited to just returning some default or some sort of response. Its code is fairly simple. I've changed the condition on the poly clause here. So remember how I used to have, if it's not a success code, you can say if it's not an internal, if it's an internal server error, you could pick any type of condition you want under which the policy becomes active. The policy is named here. And in this case, what I'm doing is I'm creating a HTTP response message, and I'm using a little bit of cached data to return. So I build a HTTP response, it's of the type OK, I put some content into it, and I return it. So if I execute a request with the fallback and I get a failure, then instead I'm returning my own HTTP response rather than the 500 or the 404 or whatever I got back from the remote system. That's all there is to the fallback. Circuit breaker. Circuit breaker is, in the US, it's like what we call circuit breakers in our homes. In Ireland and Britain, they're referred to as trip switches. I don't know what they're referred to as here, but it's a thing that would cut electricity in your home if there's a short circuit or something like that. So in the same way, this has a closed condition. Closed is the condition you want. That is like an electrical circuit, current flows when it's closed, or like a pipe, if there's no holes in the pipe, the water flows, but it's easier to stick with the electric analogy. When the circuit is open, no requests flow. Again, if you have 2 wires and they're not connected, no electricity will flow. But this has a half-open stage, and this is a test stage. After a circuit has been open for a period, it will move to half open, and that is then when a test is performed. We have 2 kinds of circuit breaker, an original circuit breaker and an advanced circuit breaker. The original circuit breaker is a simple sum of the consecutive failures. So if you get 2 exceptions or 2 404s, then it breaks a circuit. No minimum throughput required, nothing like that. The advanced circuit breaker looks at a percentage of failures excuse me, over time, and it has a minimum threshold that needs to be met before it becomes active. Circuit breaker has a way of moving around itself. It starts as closed. If you get a significant number of failures or the required number of failures, it becomes open and no more requests are allowed through the circuit breaker. The circuit breaker will immediately return an exception to the caller. So again, it's immediate. The caller doesn't have to wait around to find out there's a problem. From the open state, the circuit breaker can move to half open. And as I said, that's a test stage. The first request through the half open, if it works, the circuit will move to closed, but if it fails, the circuit goes back to open for another period. If it's been open for a period, the circuit will move back to half open, another test will be performed, and then finally it'll move to closed and your request will flow as normal. If I have, let's say, an application that's using Poly and it's connected to multiple remote applications, and each of those has multiple endpoints, I can use a circuit breaker to protect a single endpoint, a group of endpoints, or potentially all outbound requests from my application. But that would be unusual. That would mean you have some serious network problems that would be better to deal with. Circuit breaker policies work a little differently than all the others. So with a retry, as I said, you can make hundreds of requests using a single policy and they won't interfere with each other or share any state. But that is not what you want with a circuit breaker. You want the circuit breaker to share state across multiple requests so it can track the failures across all of them. If you get that aggregate number of failures across all those requests, then you want to cut the circuit. So this is easy to do with a single application because it's running in process. I can go, oh, there's been 1 failure, 2 failures, 3 failures, cut the circuit. But many of us are using multiple instances of an application that's running on containers, and they somehow need to track those failures also. I'll come to that in a moment, but I'm going to show you briefly how to write the policy. As I said, there were 2 types of circuit breaker. An original circuit breaker, and what the first one says is that if I get 2 consecutive failures in a 60-second window, I'm going to cut my circuit. Then I have 3 delegates on break, on reset, and half open, which I can use to perform arbitrary logic or do some logging, send some telemetry, or anything you like. The advanced circuit breaker says that if 50% of my requests in a 30-second window with a minimum throughput of 7 requests in that 30-second window are failures, so half my requests are failures in a 30-second window with a minimum throughput, then I cut the circuit. So it's a little more fine-tuned, probably a little bit more usable for most people's scenarios. And it also supports on break, on reset, and on half open. It's your choice to pick whichever one is more suitable, and it very much depends on your scenarios. I mentioned a moment ago that you could also have a distributed circuit breaker. So this was what we looked at with a single process making requests. But if you had something like this, multiple instances of your application running on containers, running in AWS, for the circuit breaker to function correctly, all the instances of your application need to share data. You know, how many times has an endpoint failed in the last minute? What's the total number of failures? Have I had enough throughput? You need somewhere to store that information. This feature is either been released this week or is coming very, very soon. And it uses what's called Azure Durable Functions. It lets you store state, increment in number that can be read by all instances of Poly. So think of it as a very trivial method that's got an add 1 or something like that, and then you can read. So you can increment the count. Any of the instances of your application can say, I've had a failure incremented by 1. I've had a failure incremented by 1. They all are aware of the total number of failures, and then they can all cut the circuit. Because it's not much use if only 1 or 2 of them are cutting the circuit. All right, our application now is able to isolate itself from faulty upstream applications. The circuit breaker prevents you from making requests to struggling remote systems, but it also immediately informs the callers that their requests can't be completed when the circuit's cut. So again, Poly is having an effect on upstream and downstream applications. Quick summary of our reactive strategies. We had retry, retries immediately, wait and retry puts a pause in, circuit breaker cuts the connection, and fallback returns some sort of default. I mentioned that you can combine these. If you had, let's say, a HTTP request at the center, you could perform 3 retries in the event of a failure. You could, outside that, have a circuit breaker. And if all that fails, you could return a retry. So Poly allows you to build up policies based off of other policies. I'm going to do a little demo. It's quite trivial. I'm going to have 2 screens up. On the left is going to be my local application, which is making requests to my remote application. My remote application is unstable. For most of the things I'm going to request, it's going to fail 3/4 of the time. And we're going to see some printouts on the screen showing what happens. So I'll talk you through it as I do it. Okay. I hope that text is legible, but I'll talk you through it. Again, on the left is my local application. It's using Poly. On the right is a damaged application which fails a lot. So I'm going to make a request to my local application. So what happened here was the remote application received a request from the local, failed. The local application retried. Remote application failed, back and forth, back and forth, back and forth, until the 4th request worked and I got a response. I'll show that to you again because the speed of it is quite quick. Happens very, very fast. So again, if the remote application needs time to recover, that will not help you. Instead, I'm now going to do a wait and retry. So my local application makes a request to the remote. If it works, I'd get a response. If it fails, I'm going to retry. The delays are getting a little bit longer with each retry. So the first retry waited 2 seconds, the second waited 4, and the third waited 8. This one uses a fallback. The remote application is going to fail 100% of the time in this one. So now we're making our 3rd retry in a moment. It's going to fail again. But I got back a useful OK. I chose 0 as my default fallback response. So my application can continue. It doesn't have to deal with a failure. I'm saying 0, in my case, is a useful response. It's up to you to figure out if that works for you. And then one final one, which is just to show you that for loops and try catches work. So this is one where I had a for loop to try catch, and it works very quickly, but it's brittle and hard to use. And that is my demo. Right. One moment. Oh, yes. A couple of other things before we move on to reactive strategies. Poly has a thing called a registry. We've seen a few policies so far: retry, wait, retry, fallback, and circuit breaker. If you don't want to define them every time, you can put them inside a registry. It's effectively a store for those policies. It is a dictionary, so it has all the methods and features of a dictionary. You can pass it around through dependency injection, so you could create 10, 12 policies in your startup, put them into the policy registry, put that into your service collection, and then send that around your application as needed. They are reusable, the registries, and they work with HttpClientFactory, which is quite important, as I will show you in a moment. This is what a policy registry looks like. It can be individual policies or wrapped policies, and they all get names, string names. So you'd name your retry or maybe your HTTP retry. How many of you are using HttpClientFactory? Maybe a quarter of the audience. HttpClientFactory came out, I think, about 1.5 years ago in .NET Core 2.1. It was spring of 2018. What it provides is better lifetime management. If you're using HTTP client by itself, you've got two problems that you face. If you're using a single HTTP client for all your requests, which you can do, you can end up with DNS problems, because if an IP address of a remote host changes, your single HTTP client won't know about it. But you can also end up with socket exhaustion. Sorry, excuse me. That's if you're using a single HTTP client. But if you're using a new HTTP client for every single request, you can end up with socket exhaustion. So imagine you've got hundreds of requests coming in, you're making hundreds of requests going out, new HTTP client, new HTTP client. You can end up with a problem with socket exhaustion, and it's happened at my company on a couple of occasions. I mentioned the DNS renewal. The other wonderful thing about HttpClientFactory is that it integrates very, very tightly with Poly. You can use a policy registry, as I just showed you, and then you can use an arbitrary piece of code, like a function, which could be made up of if-elses or case switches, to pull a policy from that registry based on the request you're making. And there are two ways to use the HttpClientFactory with Poly. You would start off with your service collection, add your HttpClientFactory. It's only a few lines of code. You could add a single retry policy to your HttpClientFactory. But if you're adding just a retry policy, that's fine if you're doing nothing but gets. If you're doing posts, puts, you may have problems if you're retrying, posts especially, because of idempotent concerns. But you can use HttpClientFactory with a policy registry. So you could put in 3, 4, 5, 10 policies, and then a little piece of code to pull out the right policy based on the request. And you could base it on the URL, or the verb, or some combination of those, or any other arbitrary condition you want. Quite often you'd use a retry for gets, maybe a wait and retry for puts, and you might use what's called a no-op policy for posts. No-op is a pass-through. It does nothing to the request. The code would look something like this. Configure services in your startup class in .NET Core. You would add your policies. I'm not going to show them here. You'd add them to the registry. You'd register the registry with your service collection. And then this is all you need for a HttpClientFactory. So for those of you that haven't used it, I'm naming this factory as the remote server factory. I'm giving it a base address and a default header. And then I'm saying, use a policy selector method to pick policies from a registry. And this is what the policy selector looks like. It gets passed in the registry and the request that's occurring at that moment. So every time you make a request, it'll pass through here. Every time you make a HTTP client request, it'll pass through here. If I'm making a GET request, it's going to pull that named policy from my registry. If I'm making a post, it's going to pull the no-op from my registry. And if I'm if it's any other type of request, I'm going to pull the wait and retry. So this gives you great flexibility for pulling the right policy for the right type of request, but you define it in your startup. You don't need to do it at the point that you're making the request, and then you can change it as you see fit. That is all I have on HttpClientFactory. Another topic that comes up is testing. People ask, of course.
What if you need to change the headers at every request?
That's a different type of problem, and I have a blog post about it. It isn't to do with Poly as such, but take a look at my broader blog, and it's something that came up recently. It's relatively straightforward. The question, sorry if you didn't hear it, was how would you change the headers in a HTTP for a request using HttpClientFactory if you wanted to do it dynamically? And there is a way. But for testing, testing has two general scenarios. You may want to test your code as though you're not, as though no policy exists. In that case, you would inject a no-op. So you can do your unit tests, but instead of using a retry, you would inject a no-op. If you were using a registry, you would swap, you'd put in no-ops instead of retries, wait retries, and so on. The other thing you want to test is how does your code react if Poly throws one of its exceptions, like a broken circuit exception or a timeout rejected exception. And to do that, you would use mocking. This is a talk about building resiliency, but in the last week or two, the Poly team have released what is called a chaos engine. And I'm going to very, very quickly show you that it now supports fault policies, which allow you to inject exceptions at a particular rate, and you can turn them on and off. You can inject latency, again at a rate, and turn them on or off, up to any duration you want. Or you can inject any behavior, so you could drop a database, delete a table, cut a connection. It is called SIMI. You can do, if you have access to your own business logic, you can put this code into the business logic. If you don't, let's say you're calling GitHub and you want to simulate failures, you can use these policies inside your HTTP requests so that they would interfere with the inbound response, so it would fail a certain number of times. But this talk is not about breaking stuff. All right. Let's move on to proactive strategies. The proactive strategies monitor ongoing events, and attempt to prevent problems before they occur, or they stabilize your system, or they'll let it fail gracefully, and that varies depending on your scenario. There is a timeout, which lets you decide when a request should end rather than whatever the default of the tool you're using is. Caching, which will store a response for a period, and it returns that response rather than making the external outbound request. And then finally, Bulkhead Isolation, which protects your resources so one part of your own application can't bring down the rest. The timeout policy. So if your request goes unanswered, it will time out. The choice is up to you how that happens. With HttpClient, the timeout could be as long as 100 seconds. But most of us know if you don't get a response within half a second, it's probably never going to respond. But if you're holding on to that request for 100 seconds, you're holding memory, you're holding sockets, you're holding threads, and potentially a downstream system is waiting for you to respond because they mightn't be using poly timeouts. The solution is the timeout policy. This lets you specify how long your request will wait if no response is received. And if no response is received within the period you define, Poly throws a timeout rejected exception. This can be wrapped inside other policies or outside them as you see fit, like a retry policy. It also supports a cancellation token, which will help you clean up resources that you otherwise that are in use also. Timing out quickly means your application isn't wasting resources. It's a very easy to use one and quite often overlooked. And this is how easy it is to use. This says that if you're using this policy and you don't get a response within 1 second, time it out. All right, that is failing quickly. I do have a little bit of code that demonstrates that. So in this case, my application will again make 4 requests to the remote application. The remote application will respond, but very slowly. My application is set to timeout, I think, after 1 second. So you're going to see on the left side my application timing out. On the right side, you're going to see the remote application pausing, thinking about what to do, eventually responding, but I don't get those responses. So on the left side, you see it's delaying, but on the right side, I'm performing my retries, but the retries are only allowed to take a second, and nothing ever comes back. So as far as I'm concerned, the requests failed. But you can see on the right side, responses were eventually sent. So you have to pick a timeout that is appropriate. 1 second was too short because I set the remote server to pause, I think, for 5 seconds. And what you get then is a timeout rejected exception. Okay, our application is getting more and more robust. Caching. A cache policy can be wrapped around any other policy that you're using, or it can be used by itself. The cache stored values can be used in multiple places, not just at the point you make the initial request. So you may make a remote request to a remote server to get some data, but you can use that cache elsewhere in your application. You can choose to cache the full HTTP response or just the business data. That's up to you, and I have a bunch of examples on the blog about that. How it works is a little bit more complicated. So in configure services, you define the cache. In this case, it's a memory cache. You set a relative time to live. In this case, I've set 30 seconds. You can choose different types of timeout. You can have absolute timeout, sliding window, result TTL. So result TTL is great if you're using something like a JOT, and it comes with a HTTP response header that has a timeout. You define poly context, and what you'll notice here is that I'm saying I've got a static part of it defined, and then I've got a dynamic part. So I'm storing something in my cache, which is a combination of these two names. So it'll be get by inventory ID number 5, 10, 15. So if I get a request for the same one, I'll read from the cache. If it's not in the cache, I'll go to the outside service. And then this is how you use it. You say cache policy.execute async, and then you do the HTTP client request. It's difficult to use the cache with HttpClientFactory. This is something that I've talked with Dylan about, and they're probably not going to change it. So if you want to use cache, you're better off to use policy registry, put it into that, pass the registry into your controller or whatever code, and then wrap the call to your HTTP client just like that. This example shows the caching of the whole HTTP response. You can, as I said, cache just the business data. It's a little more complicated, but I wrote a 3-part series on my blog on how to do that, and also how to selectively cache. So this will cache if you get a failure too. But it's not trivial to do it to only cache if you get 200s. But as I said, I have a bunch of examples on how to do the selective caching and how to cache business data only. So please take a look at that. Because it's a cache, it has all the standard methods you would expect from a cache, like on cache get, on cache miss, put, error, and so on. Okay. We're getting more and more resilient with our application. And we're down to the final thing on protecting resources. So this is what happens if your application can't handle all the incoming requests. Memory will be used up, threads and sockets are going to be held, and this can bring down your whole application, but it could also affect downstream applications because they're making requests to you, they're expecting you to respond, you're not responding, they're holding on to memory, they're holding on to sockets, and that can have, as I say, a broader effect. The term bulkhead isolation comes from the nautical world. So if any of you have sailed boats or done worked on large ships, you'll know that they're broken into bulkheads that are isolated. So if I was to puncture a part of the ship here, this would flood, but hopefully the other parts wouldn't flood. So the same analogy, if one part of my application is having trouble, hopefully I can protect the other parts of the application from getting into trouble, and my whole application or my ship will not sink. How it would look, I'm going to go back to this little local and remote example. If I have a local application that's calling a remote application, making requests, 1 request, 2 requests, no responses yet. I get 1 response, it's good. I never get the second response. Now I have 1 request hanging out, holding on to memory, holding on to threads. I make a couple of more requests, I only get 1 response. Now I have 2 outstanding requests. I make a couple of more requests, I only get 1 response. Now I have 3. So imagine this continuing on, and I'm holding on to these resources, and I'm only getting some of my responses back. Eventually, my application will fail if you're doing this at a high enough rate. There's not much else that will happen. It will bring down your application. So this is what the poly bulkhead looks like. It's made up of two parts: execution slots and queue slots. As the name implies, execution slots are where requests are executed, and queue slots are where you store the next requests that are going to be executed. Let's say I get 3 incoming requests. None of the slots were in use. Those incoming requests are immediately put into execution slots and start executing. Now let's say before those 3 or any of those 3 complete, I get 6 more requests. They cannot go into execution slots, so they go into the queue slots. Now I've got 3 ongoing requests and 6 queued requests. I cannot take any more requests, but one comes in anyway. That will be rejected with an exception immediately. The system that calls me will get a bulkhead exception immediately. It'll know I cannot handle another request, so it can do whatever throttling that it needs to perform, and my application doesn't suck up more resources. Because I'm never going to have more than some specified number of execution slots, I'm probably helping the upstream system too by not overloading it. So again, I'm helping my own application. The downstream application gets errors immediately, and the upstream application is being, I'm throttling my request to the upstream application. So again, resiliency is across the spectrum. Let's say one of my execution slots frees up. Great. One of my queued requests, excuse me, I'll try that again. One of my queued requests will move to the execution slot, and now I can take another incoming request. And the same process continues. I'll only execute a certain number, I'll only queue a certain number, I'm only going to take up a certain amount of resources and nothing more. Bizarrely, for a complicated thing, it's written extremely simply. I'm saying that this handles HTTP responses. I've got 3 execution slots, 6 queued slots, and then this is a delegate that I can use in the event that everything is full. And you can use that for logging, for scaling, for anything you want. How this would look across a whole application would be something like this. Let's say our application's up and running, and let's pretend that whatever amount of memory, threads, and sockets we have left is 100%. You know, obviously, it won't be that for the whole computer, but let's say it's 100% of what will be available. And let's say I've got 12 different bulkheads. It would look something like this. As you're getting requests coming in to various parts of your application, you're going to limit how much of the overall memory, threads, sockets, any part of that application is going to use. So no matter what happens within your application, you should be able to contain the amount of memory and the amount of resources so that you'll never run out. And hopefully your application remains stable. All right, that is the last thing that we needed for our little application. So hopefully we have a fault-tolerant, resilient application. If you want more information, I have a Pluralsight course on this. I updated it 8 or 9 months ago to include information on HttpClientFactory. It has examples of all of these. I have a blog with far more examples and slightly newer stuff. Particularly the caching one is something that a lot of people have been asking me about. There is an active Slack channel. I'm on it from time to time. Dylan is on it all the time. Dylan, the gentleman who is running the project at the moment from the code perspective. Steve Gordon and a few other people. Some of you may know Steve. He does a lot of writing on HttpClientFactory. There is a GitHub that you can raise issues on. You can contribute if you can. That would be wonderful. They're always looking for contributors. And then they have a blog as well. I'll put this slide up again in a moment for you. I want to thank you all for coming out. I will stick around for questions or if anyone wants to know anything else. But other than that, it is a wrap. Thank you very much. Thank you.